Hello. Alright, so today I've got a bit of a longer video planned. So the topics I want to go over is I want to introduce like balance, which is a semi-new concept. And with that I want to do regular and irregular quadrants. I want to do inverses and ghost numbers, and I want to do balancing other sorts of regions, as well as briefly going over offsetting and splitting. And then next I want to move on to RSB and the alternate rule, and a special case of it as well, but I didn't include that in the plan. And then I also want to do skewed numbers with the same number I'm going to start off with to like motivate it, and then I'm going to generalize it, and then I'm going to relate all the topics is the plan for this. Alright, so we're going to quickly start with the very basics. So if you have two blues on this side, this means that on the other side there must also be two reds. Instead of thinking like normal, like just two on either side, I want you to think of it as plus A on this side and then plus A of the other color on the other side. This is fundamentally just the same thing, but there are some benefits you get thinking this way later on that you'll see. Likewise, you can also do the same thing if there are two rows instead of just one. From now on, I'm not going to actually draw the circles back in, just think of it as plus A on either side. You kind of know what that means by now. We're back into more interesting territories here with the quadrants we all know and love. Now, instead of thinking of both the numbers inside the quadrants, we just have one number that represents both of them. And of course, like usual, you can mirror them down like this. Sorry to speed through this section so fast, I'm just hoping that you already know what quadrants are from previous videos or just experience with the game. Now this is where stuff gets a little bit more interesting than just the basics. We no longer have to just work with the easy symmetrical quadrants that we're all used to. Like in the previous ones, we're going to start up here and put plus A in here, which isn't necessarily anything in specific, it's just a variable. But then we can move over here and then put plus A here, and also down here as well. Due to the fact that the blue quadrants both have the same size, it means because they both have plus A, they end up both having the same amount. Unlike the blue quadrants, these red ones don't have the same amount due to them being different sizes. However, we do know a lot about the relationship between the two of them. Let's move into the first interesting example where we start off with 4 of one color in the top. This is the worst case scenario for knowing the maximum in a 4x4. 4 times 4 is 16, so I just quickly half that to get the expected number if it was half-half. As the difference is 4, I minus 2 and I plus 2 to get the two different amounts for the two different colors. And obviously the difference is 4 between these because 6 plus 4 is 10. So how many reds are in here? Well, there's 10 reds in here because there are 4 more reds than there are blues, and there are 6 blues. This is equivalent to saying no 4x4 has more than 10 of a color. Okay, so now what's the best case? The best case is obviously when they're balanced, which means they'll have the same amount of reds and blues, which is 16 over 2. When would this occur? This would occur when there's a 1 in the top corner, or if you just knew all the things in the slot. Next, we're going to move on to inverses. What is an inverse? Well, an inverse is like the exact opposite of a number in Urjo. A number, including all the 8 slots around it, has a total of 9 slots. If inverses are the opposite color, they have the exact same number of reds and blues. Handily, there's also a pretty easy equation to figure out what the inverse of any number is. And the equation is just 7 minus the number you're working with. In a 6x6 like this, there are only 3 sets of inverses. Like I said earlier, inverses that are opposite colors always have the same number of red and blue, which means they have this very nice property here. As well as this property, where they have to be the same color if they're next to each other, they're also the only two numbers that can be facing off in quadrants like this. Obviously, the other option being they can face off against themselves if they are opposite colors, which is also allowed. It's also worth knowing that on the diagonal quadrants, they have to be opposite colors. So this one on the left is adjacent to the 6 above it, so it must be red, and it's also diagonal from the 6 upright of it, which means it also has to be red. Repeat for the other one. A quick detour here to ghost numbers. Ghost numbers is just the idea that every slot has a number assigned to it, but we don't necessarily know what it is. So if we've got a 6 here, over here we can deduce from before that we either have a 1 or a 6. And for example, if we had a 5 down here per se, which is obviously not possible because the 6 above, but if we did, then over here there would either be a 5 or a 2. This doesn't just apply to quadrants, but this is the main way we'll be using it today, so I'm not going to do any other examples. Now I'm going to go back to balancing and show you can balance regions that aren't quadrants. I'm just going to quickly go through and put in all of the like plus A's and stuff, which is pretty useful information. This second example is almost quadrant-ish, but it's technically not a quadrant. Because the limiting factor is always the smallest one, and there are 2 that is the smallest one, you can also put the plus A's into the second one. So I'm going to go back and put the plus A's into the first one, but just remember, it's usually the smallest one that's the most important for how much they can differ. The third one also has the same property where there are 2 of the smallest one. I'll just do maybe one example, probably the first one with real like numbers to show you the maximum and minimum, and then you can just figure the rest out for yourself, I think. So the maximum variation you can have is 2 in the first one because there's 2 in the upper left. This is a 4x5, so there's 20 maximum cells, so half of that is 10. Due to the variation from the top left, this means there's going to be somewhere between 9 and 11 of each colors, obviously reflecting each other. If one's 10, the other one has to be 10. If one's 9, the other one has to be 11, that sort of thing. If you want, you can look for the maximum of this one too. This is a kind of important one because if you have like a 2 against the wall, you can have the entire like red box filled with half-half, so it can be quite restrained. Especially if you have like a higher number in the bottom right quadrant. So now I'm going to quickly return to quadrants again to show you offset quadrants. So this is a sort of normal quadrant where you have plus A here, and then you have obviously plus A over there as well. But quadrants are kind of just one specific version of a more broad class of offset quadrants. So like in these 2 sections here, you have plus A, and in this one section here, you have plus A as well. And likewise, in this final one, you can do the same thing. And then also in the bottom, you can carry this on and fill them all in. You'll notice this really just works the exact same way as quadrants, except it's just a little bit offset. Oh, but you think we're done generalizing yet? No, we have this now. These are called split quadrants. I've heard them occasionally referred to as exploded quadrants as well. It's a little bit redundant, but I'm just going to put the plus A's back in here because I've made the quadrants different colors to make it a bit more obvious which one's part of which quadrant, especially for the 2D split. This effectively just really functions the exact same as the other quadrants. Wherever anything's on a diagonal, it'll be the exact same. There's a broad section of rules that work across all classes of quadrants, but it is important to note if rule 3 is used and you split them apart, then rule 3 obviously won't still apply and it won't still work. Congratulations on making it through section 1.1. We are now on to section 1.2, which is RSB. RSB is a rule that describes the behavior of 2 numbers right next to each other. Let's start with an example of 1 and 3. First, let's add the numbers together. Next, we're going to need to figure out how many slots are shared between the numbers. In this case, it's this 4 here. Now let's quickly write down this into the equation. So this means the red of the red number and the blue of the blue number, when added together, is equal to 0, because once you move the 4 to the other side, 4 minus 4 equals 0. This means that the red of the red number is the negative of the blue number, which means they're opposites. So let's say that 1 is the blue number, and let's say that it has no blues. If there are 3 reds below it, because it has no blues, it means above the 3, there's going to have to be 3 blues. It is worth noting RSB only applies when they are opposite colors. It is also worth noting that RSB doesn't have to have the numbers be right next to each other to give information. Let's say, for example, we have a 4 here and then a 3 up here. RSB can still be applied because there are 2 slots overlapping. So just like last time, let's plop this back into the equation and see what happens. As you can see, r plus b is equal to 5. What does this mean in practice? Well, if the 4 is the red and the 3 is the blue, then if we look at the regions, this is the region around the 4 that's not shared, and up here is the region around the 3 that is not shared. So let's try putting in some actual numbers for this. Say around the 4 there are 3 reds. And then to get to the total of 5, which is the reds plus the blues, we need 3 plus 2. 2 being the number of blues around the 3. We don't actually know the position of these reds and blues, but I'm putting them around so that you kind of see the area that they're in. The relationship between the 4 and the 3 is really well shown in this example. There are also some obvious upper limits. Obviously the first number can't go above 4, so it can't be 5 and 0 because the 4 would be maxed, and the second number can't go above 3. RSB only works if the two numbers are different colors, so what happens if they're the same? That's where the RSB alternative rule comes in. Instead of having red and blue, we now have the red that are not shared from one side and the red that are not shared from the other side. There's not really a nice abbreviation for this that anyone really has used that I've seen, so I'm just doing NSX and NSY, standing for non-shared X and non-shared Y. And then in this example, I'm going to use C1 and C2. So first we do X minus Y, and that's 5 minus 4. And then this is the same as C1 minus C2. To show how this works, I'm going to put 2 in the shared region. Obviously, we wouldn't actually know these were here in practice. As you can see, the 4 needs 1 more, and the 5 needs 2 more to get to its number. As you can see, this rule holds, as C2 has 1 less than C1. Okay, so this is about to get a bit more technical, and you won't quite understand yet why this is important, but this is used quite a lot later on, so it's worth going over. So we're going to start off with normal RSB. And then we're going to replace y with its inverse, if you remember the equation from before. That being 7 minus the number itself, as you can see here. After that, you need to quickly rearrange the equation so the 7's on the other side and the y stays on that side, but it's minus y now. This rule is only intended for 4 slots, because it's a special case, so we're going to sub in 4 slots here. And then 4 minus 7 is going to be negative 3. In this situation, there are 3 slots that are unshared. 3 minus the number of blues is the same thing as the number of reds. B minus 3 is the same thing as minus 3 minus B, which is the same thing as minus the number of reds. This might seem a bit miraculous, but as you can see, this is exactly the alternative rule of RSB. This means that in the case with 4 shared slots, if you take the inverse and then make it the other color, it won't change the outcome. If you look to the right, you'll see an example where 5 gets changed to its inverse of 2 and the color gets switched, and it ends up being the exact same as if it was still the 5. This is kind of interesting by itself, but not the most useful until later on, where we're going to use this to show some very important things. This is not to say it's completely useless, because in the case of 4 shared slots, you can kind of just use the opposite rule if you take the inverse and change the color, instead of using the other rule, which can be kind of hard to remember both of them. Either that, or maybe you're faster with running the rules than the other rules, so you can do this to save some time. Okay, so moving on to section 1.3 now. In this section, we're going to make some observations about skewed numbers. First thing that you can notice, due to the mirroring of the quadrant, is that there are in purple in this box here, and there are also in purple in the box below it. Due to this mirroring, you get a very interesting situation where the middle 2 are always the same in both the top and the bottom box, which means that the top box has to be the same as the bottom box. And finally, I've just moved these 2 over here so you can see more obviously the ones that I'm talking about. This pattern is also symmetric, so the other side, you could put orange boxes there if you wanted, would also be the same at the top and the bottom. And now a quick example. I'm going to use 4 as our n in this example. I am also going to give the 4 slots below the red 4 so that you can see how this works. By this rule, this instantly implies that these 3 up here are also going to have to be blue. As you can see, this also necessitates that the other side must also follow this rule, because it's opposite. Obviously, this often won't have 3 of a color directly below one of the numbers, but it does mean, like, if there's 2 on one side and 1 on the other, then the one above must have 2, and on the other side, the one above it must have 1, that sort of thing. Here's a quick demonstration inside new so that you can see what it sort of looks like. As you can see up here, you can no longer have 3 of anything, and the only thing you can have 2 of is blue. So although they are no longer like lined up like they are in the 3 case, it still always has to be this number. This definitely has some uses, but next we're going to generalize this further. Okay, so now we don't have n and n any longer, we have n and m, where n and m are not necessarily the same number anymore. Like last time, we want to look at the top and the bottom due to these squares from the m. Now, if you remove this orange section from the m and then add the green section in, you get n. Now you need to just do some quick rearranging and you can easily see the rule. Now, if you are paying attention, you might have noticed something interesting. We have seen this formula before in the RSB alternative rule. If we use quadrants to reflect this over, we can get one of these two options. Now, if you remember this proof that I did earlier, these two options actually end up being the same thing. This means, well, kind of exactly what we said before. Technically, you can also use just normal RSB rather than the alternative, but that's way longer and way harder to do. We can quickly look at what the special cases are. The special cases are when the numbers are the same, the top minus the bottom equals 0, so the top and the bottom are the same, or when one number minus the other number is 3, then they are the opposite. Let's quickly go back into Urjo/new so we can take a look at how this looks. Okay, so we start off with the numbers being the same, and as you can see, you must have the exact same on the top as on the bottom. And then after this, we're going to switch to where it's 3 less, so you can see that special case as well. 3 less than 5 is 2, so we can quickly put this in. There are some more interesting things that I can say about this 5 and this 2, but I can't quite say them yet because we haven't got up to it. Anyway, now let's show another difference of 3. As you can see, they're always forced triples because 3 minus 3 equals 0. If you have 2 or 1, you can't have a difference of 3. This is also interesting because if the colors are opposite like this, it means that the maximum difference between two numbers skewed like this, where they are different colors, must be 3. What does this mean for us? Well, this means if the difference is bigger than 3, then the numbers must be the same color. Of course, there are other ways to work this out, but this is quite an efficient way to do it because you can just remember the number 3. Okay, so we've now got the special cases out of the way, which are kind of the most important thing, but we can also look at what happens when it's not one of the special cases. Okay, so I've chosen numbers 1 apart. This means the top must be different from the bottom by 1. As you can see, because there's 3 on the bottom, that means above there must be 2 of that color. And then we can quickly fill the rest in and show the full pattern. As you can imagine, due to the fact that this relies on the alternative RSB rule and also RSB using the inverse, we can also tell things about those two situations as well. As you can see here, if it differs by more than 3, it gets forced to be the opposite color instead of the same. Remember, due to the mirroring, we are now looking at the same color instead of opposites. As before, if they're the same number, it mirrors down, and if they differ by 3, then they must be opposites, and also it's forced triples. Using the inverse and opposite colors, you can use the same rules. Inverting the 3 and swapping the color holds the same rules here. Now that we've related RSB to skewed numbers, we can also do something when they're the same color. As before, this equivalence means we can either look at RSB or the alternative rule. This time RSB is easier because you no longer have to work with the inverse. Now you might be recognizing this special case from just before. If you add a number and its inverse, you will always get 7. This is because the number itself, plus its inverse, which is 7 minus the number, has the numbers cancel out and it just equals 7. So you can either check if the number is next to its inverse or if the numbers add to 7, which is logically equivalent. Like this, we can also use the inverse to get the difference of 3 that we saw earlier. You'll notice that upon doing this maths, you'll end up seeing that it's 4, like we've got over there. The links between RSB and the alternative rule in terms of the special cases when there are 4 overlaps are quite similar, quite linked together. For this one, I'd recommend just remembering they add to 4 rather than thinking about the inverses, but you can technically think about it either way. Alright, so this is skewed by 2 instead of 1, but you can actually think of it as being skewed by 1, but down here, because you can mirror the M down to here. It'll switch colors, obviously. And then this is the skewed number that you then can mirror over beneath, and it's either M or the inverse of the other color, which, as before, due to the proof that I did earlier, means these two things have the same for the above and below boxes. You can treat this the exact same as skewed, just don't forget to mirror the colors so they're not the same. You can also note that everything that's skewed by 1 is also skewed by 2 if you use the same quadrant mirroring idea. This means that if there's any information to gain from 2 skewed, then 1 skewed also has this information, and vice versa. So this is what we're going to look into next. Firstly, we're going to naively assume the same connection as before. However, this quickly runs into issues. We can see this by rearranging the equation on the left. The reason we subtract 5 is because this is the number of unshared slots that there are. This means that we can turn b minus 5 into the negative amount of reds that there are, and then just some final rearranging to finish off. Now we have r1 minus r2 just like the equation on the right, but you'll notice that they're actually not the same. This is because when two numbers are right next to each other, it's a very special case scenario like I mentioned earlier. So what are we actually going to do? Well, instead of how we were dividing it up before, we're actually going to divide it up like this. And we're going to link this red box to this blue box using the small 1x3s here and here. I'll start off with just the equation, and here's the equation here. This equation has assumptions, but it doesn't lose generality. First, we want to assume that m is the difference between these two boxes. And then we're also assuming that we're counting the least common color. Since we are counting the least common color in the 1x3s, that means that it's the most common color in the 2x3s. So there must be at least 6. Now why is this? If you add all of these boxes together, you'll get 9, and then you can move the two 1x3s to the other side. Then we assume that green is the one with the least number of that color. That means that purple is m plus green. Finally, if you substitute that in, you get 9 minus m minus green, which is what we have at the top. Okay, so there was a reason we assumed that this was the least common. That means when we look at the difference of 2, we can choose the least common and then say they're actually the same thing. We can then do the same for difference of 3 as well, and say that there's only one option. Unfortunately for 1, there is actually 2 options. 2 different ways you can have a difference of 1, and the same thing applies to a difference of 0. There are 2 ways you can do that. Okay, now we use the fact that we're picking the least common color to pick the least common 1x3, and that's the one with 3 purples, which has 0 blacks in it. If we then use the equation, which is 9 minus m minus the difference being 0, we get 9 minus 2 minus 0 equals 7. And here we have 9 minus the difference of 3 minus 0, which is 6. 0 once again coming from the fact that we can pick, for example, the triple purple, which has 0 blacks in it, which is the one we're hypothetically counting. Difference of 1 splits into 2 options. One where we have 0, and one where we have 1 is the minimum, which gets used twice. And then finally doing the same for the difference of 0. To summarize, this is what we know based on the difference, how many there are in these two sections. And finally, let's find a link between the diagonals with the 2x3s. Firstly, this is the equation to get from the red box to the pink box. And then we bring the equation to link these two boxes here back in. Finally, we can just link these two equations together by substituting in the red box for the pink box and then simplify down to this. Okay, so when are the interesting points where this comes up? That's when m plus the least color twice is 3. What this means is that purple and pink are the same. And when does this happen? This happens when m is 3 or when m is 1 and the least is 1. And this works for the other way as well. So we end up with this sort of quadrant shape where instead of the normal 3x3 quadrants, we have a 2x3 quadrant. Now I'm going to show you how this looks in practice with some quick examples. Let's start off with the special case with a difference of 1. I'm going to show an even more special case where, because they add to 6, the top and the bottom are the same. As you can see, you can't have 4 of either color down there, and then we can quickly just add in 3 and it fills in all of the slots. As I mentioned, this is a very special case, and as you'll see, all of the 2x3s end up having to have the same counts. And now I'll just quickly run through one and the same with a difference of 3. Difference of 3 is more useful because you know that it's always going to follow this rule. This time we're not going to do 3 and 3, I'm going to do 4 and 2 to show off more of the quadrant-like capabilities of this. Over here, there's going to be 4 reds, so we can show this by just putting in 2 blues here and then 2 reds at the bottom, and it just fills in the rest. You can't put any more than that in. And then I'll show an example of a not special case. Obviously in practice you can just do the maths here, but we're assuming that in reality you'd be working with numbers and you would know the difference, but you wouldn't know how many there are in here. So 9 minus 1 is 7, so the total is going to be 7, so we instantly know that down the bottom, because there are 4 up here, there has to be 3 blues, and we'll put that in, and then you can see there we've got all 7 of the blues in. In practice, you'd want a difference of 3 or a difference of 2, because then you would know for sure how many of the least there are in each. But if it's a really difficult one, you could maybe assume that the difference is this, or that the difference is the other one, and then work from there and see if you can find contradictions. And there we go, we're done. Yippee! If I've made any mistakes or haven't explained anything well through this video, feel free to come and message me in the Urjo Discord server. I will probably respond and try and help. I hope you enjoyed and that it was fairly understandable. If I discover more strategies, I'll probably make some more videos in the future, and if I don't find any, then maybe not. Alright, bye.